Hello Math 4411 students. Let's begin Lesson 7, Direct Products and Finitely Generated Abelian Groups. First, direct products. We begin with the Cartesian product. Given n tuple of sets S1 through Sn, we define the Cartesian products S1 times S2 times and so on as a set of all n tuples A1 through An where each ai is an element of Si. This is called the Cartesian product, but there's a bit of a problem. How do we define this n tuple? That's a big problem. Do you recall how difficult it was to define a pair? If you do, great. Even if you don't, well, here's a reminder. A Cartesian product we want to define like this, but there's a bit of a problem. What's the starting set so that this Cartesian product is a subset of that set? If it is unclear, then this set builder notation is invalid. So how do we get that? We define an ordered pair like this using the set theory notation and the axioms of set theory. Here I use the axiom of power set and the axiom of union. Now that this is well defined, we can use the set builder notation like this, and now we have appropriate set here, the starting set, and the Cartesian product is a subset of that. So the set builder notation is finally valid. So we have Cartesian product. Come back here. Can I do that with 3 sets, 4 sets, or arbitrary n sets? Well, it's not that obvious. So how do you do that? Let's go back here and we define the Cartesian product. Yes. And then we define a relation as a non-empty subset of a Cartesian product. Remember all that? And then define a function as a special relation with this property. Given element in the domain, there exists one and only one element in the target that can be paired with the element in the domain. With this property, you can define a function. Okay. Cartesian product of 2 sets, relation, function, all done. Will those help us here? Yes. We're going to define this n tuple as a function like this. A is a function defined on a subset of integers 1 through n to this union, and union is always well defined. Remember the axiom of union. S1 through Sn are well-defined sets. They are given sets, so the union is always well-defined, so that you can define a function like this, and that function is the n tuple. So yes, this is now well-defined and we can use it. By the way, you can extend this idea to infinite tuples as well for arbitrary index set capital I, which can be infinite. And to be a little bit more precise, you can define your function like this. But the index set capital I may not be well defined in some cases, so you'll have to use another axiom of set theory, the axiom of choice, so that they can be arranged in a good ordinal order. But come on, that's getting a bit too deep, so let's stop there. Let's just be satisfied that we got through with this Cartesian product of finite tuples perfectly well, and then we got 99% of this as well. Okay, so much for Cartesian product, and remember they are now rock solid. Now let's go to direct product of groups. Let G1 through Gn be groups, and that's Cartesian product forms a group under the group operation induced from those of G1 through Gn by taking component by component. A1 times B1, A2 times B2, ai times bi all the way over to an times bn, component by component. And of course, it doesn't have to be a finite Cartesian product. If you have appropriate index set with everything well ordered, then we can do component by component computation so that you can consider infinite tuples as well. To be really precise, you need an axiom of choice, but in any case, we'll have all those. As for the proof that this is actually a group, that's embarrassingly simple, because we are doing all those component by component. So for ith component, we have associativity, of course, because it's a group there. And then the identity, well, we take identity elements for each component. And same for the inverse. Inverse for each component. The detail is left to the students. So we do have direct product of groups, and in a special case, we may use the term direct sum, especially when we have abelian groups. Then we sometimes use sum notation instead of product notation. That makes a lot of sense because preferred expressions for group operations for abelian cases addition symbol so that it really looks like commutative. But even for abelian case, our textbook author uses this cross notation and this product notation most of the time. I think all the time, So I'll try not to use these expressions in the right-hand side. Okay. So we got the direct products for those. Now, do we have enough time to do this? 1.3, direct products of residue classes. Well, okay, I think we'll have enough time to do some examples, but probably not enough time for the theorem and its proof. Okay, let's consider the general case. So the direct product Zm times Zn is defined like this. Zm is 0 through m minus 1, the residue class, and Zn is 0 through n minus 1, again the residue class. Consequently, each element looks like this, a bar comma b bar, where a is coming from Zm, so between 0 and m, and b on the other hand is between 0 and n. Make sense? And then this can be decomposed into A0 plus 0b. Yes, pretty clear. And finally, A times 1, 0 plus B times 0, 1. So this is coming from Zm, that's coming from Zn, but this 1, 0, well, mostly came from Zm, so I'll just continue with color coding blue. And 0, 1 mostly came from Zn, so I'll use the color coding of purple here. Because, 0 times something stays as 0, so the first component is not there, and also same for here, second component does not contribute. So in short, every element can be written as some integer times 1, 0 plus another integer times 0, 1 form, where those integers a and b are non-negative integers between 0 and m and between 0 and n respectively. These are integers, so basically this one is actually repeated addition a times, and then this one is repeated addition b times. So everything is coming from a repeated application of the group operation. Starting from these two elements, blue and purple. For that reason, we call these two elements the generators. Now the question is, Is it possible to reduce the number of generators from 2 down to 1? That's a question here. With 2 generators, yes, we can express everything. If you have Zn times the n times, well, something else, Zs for example, then you're going to get 3 generators. If you have product of 17 of those, then I'm going to get 17 generators. And can we reduce those 17 generators down to, say, 14 or 6 or 3, whatever? Can we do that? That's a kind of question I'm asking. Of course, not that complicated, but for simpler cases. Z2 times Z2. Of course, there are 2 generators, 1, 0 and 0, 1. Can we bring it down to just a single generator? The answer is no. Z2 times Z2, or also known as Klein's 4 group, has this structure: 0, 0, 1, 0, 0, 1, and 1, 1. And 0, 0 is, of course, identity, so that's trivial. And if you take any non-trivial elements, we get this cyclic subgroup, the second cyclic subgroup, and the third cyclic subgroup. None of them covers entire V. So there's no cyclic subgroup that covers entire V, so V is not cyclic. So you cannot reduce it into a single generator. How about next, Z3 times Z3? The answer is no again. Here, 0, 1, 2 for first component, 0, 1, 2 for the second component as well, so we have 9 elements. And then 0, Z is non-trivial element, and then 1, 0 will generate this cyclic group, 0, 1 will generate this cyclic group, 1, 1 will generate this, and 2, 1 will generate that, and then you don't need anything else because these cover everything. For example, 2, 2 is already in there, and then 1, 2 is already in there, etc. Everything is covered. In short, there is no cyclic subgroup of order 9 that covers everything. So Z3 times Z3 is not cyclic, so the number of generators cannot be reduced to 1. Now how about this, Z2 times Z3? The answer is, this time, yes. We have these 6 elements, and then if you start from 1, 1, let's say 0, 0 plus 1, 1, so we get that, and plus 1, 1 again, you're going to get 2, 2, but first 2 is congruent to 0, so we get 0, 2, and a plus 1, 1 again, then 1, 3, but 3 is congruent to 0, so 1, 0, and plus 1, 1 again, plus 1, 1 again, eventually we cover everything. So this group is generated by this 1, 1, so it's cyclic. So successfully we reduce the number of generators down to 1. When is it possible and when is it not? Well, let's state the theorem and we'll prove it in the next video. It turns out we can reduce it to a single generator when M and N are relatively prime. Applying this repeatedly, the direct product group of, well, this N residue classes is cyclic if and only if each pair is relatively prime. The proof will be discussed in a separate video. We don't have time now.